Welcome to Alaska Earthquake Science Facts. I'm Carl Tate. The first large-scale computer simulations of a San Andreas Fault scenario earthquake used the 2002 Denali earthquake as a realistic model. I'm going to play this movie off of YouTube to try to convey what a computer simulation of an earthquake might look like. This one is for Southern California. So you'll watch the timestamp down here in the lower right. It'll advance quickly, so it's sort of sped up from real time. And the color is showing you the ground velocity, and you'll see this earthquake rupturing and moving to the southeast. So here the earthquake initiates, propagates in both directions, but mainly down the San Andreas Fault to the southeast. Here's the Los Angeles region right here, and propagating, continue to propagate. A lot of wave motion still sitting around, lingering in Los Angeles as this continues on. Still finishing there at about 180 seconds down there at the end. So 3 minutes and still there's ringing around. So this movie is a spectacular display of both the visualization but also the computation behind that complexity. So what is a seismic wave field computer simulation? It's a calculation performed by a computer, often a supercomputer of thousands of machines, that solves a mathematical differential equation describing how waves propagate in a solid material. Both the earthquake and the Earth's three-dimensional structure need to be quantifiably characterized for the computer. The output of the simulation is the seismic wave field, which is the direction and size of ground motion as a function of time at every point inside the simulation volume. So tracking how the ground is moving as a function of time. The simulations can be used to provide estimates of ground motion for scenario earthquakes, which are earthquakes that are plausible in the future. So the focus paper is from 2006, strong shaking in Los Angeles expected from southern San Andreas earthquake. And the word expected is really to say we expect certain ground motions by using accurate computational models that take into account the complexity of the Earth's structure and also consider realistic complex earthquake source models. So in this paper, we see the line, the source model is based on that inferred for the 2002 Denali earthquake, magnitude 7.9, the only instrumentally recorded strike-slip earthquake in North America with magnitudes similar to these scenarios. This shows the paper based on the source model they used, published in 2004, where they looked at performing what are called kinematic and also dynamic models for the Denali Fault. Basically looking at characterizing the frictional behavior along these faults, or instead using distant data to obtain a kinematic model, which is a description of how things slip on the fault. So in this case, they have a complex model based on the geology and other information of starting on the Susitna Glacier, the Denali Fault in these segments, and then also this Tachunda Fault, which we've seen in another Alaska earthquake science fact. So here's the model that was estimated, and now this is going to get moved down into Southern California to try to get realistic picture of what ground motion might look like there. And this shows the final amount of slip for this model. This shows across each fault segment. And so this is inferred from recorded seismic and geodetic data. And the scale down below is shown in centimeters. So the yellows here are looking at, would be in 12 meters of slip, the greens in 10 meters of slip. This shows distance along the fault segment from that previous fence diagram. And this shows the depth. So we're looking at sort of down to 30 kilometers depth. And you have these slip patches that are up to 10 meters of slip. So the result of the simulation and that the authors were looking at is examining how if we change the direction of the rupture still the same size earthquake, but how does that change the ground motion? And they found these very big differences. So from southeast to northwest, coming toward the northwest, they get this large amount of ground motion, peak ground motion in the Los Angeles area, whereas going from northwest to southeast, it's a very different story. So that shows the kinds of complexity, the outcomes that can arise when we take into account all this complexity. It matters which direction the rupture moves, and it's going to matter in terms of what you prepare for if you know whether one direction is preferred over the other. So that shows kind of one of the more interesting outcomes from exploring that simulation in that study. These were done by a team with the Southern California Earthquake Center, and to show kind of how things evolved since 2006, the next big leap was a more holistic model in Southern California where they're looking at all kinds of different sources, randomly generating realistic large sources on faults in Southern California, and trying to understand what that means about the expected ground motions at different places in Southern California. So this was published in 2011. And this shows what one of those source models look like for a magnitude 7.65. This is depth. This is a function of time. These contours, sorry, of distance. And these contours are showing time, how the rupture evolves from its epicenter. And the color here is shown in slip, where in this case, there's a slip patch that is about 10 meters, but most of it is in the sort of 4-meter range, low down deep in the crust. And this shows an example, 6.65 magnitude 7 earthquake used in that study. The outcome was to say that taking into account simulations or not gives a different picture for what the peak accelerations are expected in different regions of Southern California. So the point is that taking into account more physics gives a different perspective from the calculations or estimations that are based on more approximate methods. In 2021, stepping 10 years forward, a real big step to look at, again, using more source complexity, use the frictional properties of the faults, which change from one earthquake to the next, to model the future earthquake ruptures. So kind of take into account in your building of all the possible scenarios, the influence of all the past simulated earthquakes. So it's trying to get a more physics, as it says, physics-based seismic hazard model. And just to show some of the figures here, this is showing the three-dimensional view, this fence diagram of faults in Southern California, and an example of one of the earthquakes in their model occurring on the southern San Andreas Fault. They also show, a really complex example of this kind of fault interaction with low-lying flat kind of faults in here, as well as steep dipping strike slip faults. It says, here's an example of one of the earthquake ruptures. It nucleates on the Compton Fault. Here's this low-lying fault. Then it spreads to the Newport, Inglewood, Palos Verdes, and other nearby faults. In total, 10 different fault sections participate in this event, but 3 account for most of it. So it gives you an idea of the complexity, and this complexity is real. This is the kind of best picture of the fault, at least systems that are underneath Los Angeles. So the takeaway topics, first is that computational simulations of scenario earthquakes can provide realistic predictions of long period ground motion. Also, the 2002 Denali earthquake was one of the largest and best recorded earthquakes in the modern post-2000 era. And in this case was valuable as an input for understanding what could be possible in Southern California, where they have not had that kind of an earthquake in a long time. So thank you for watching. Stick around for a supplemental slide.